Hi, welcome back to the NonSequitur Show. We have got an amazing episode for you all today. This has been a culmination of about a few years worth of stuff on this particular topic. We go way back 4 years when I think it's been at least 3 or 4 years. I think it was in 1919 or 2019 or 2020, if I'm not mistaken, when I had last had these two guests on talking about this particular topic. It is a canard that comes around every so often. And to give you a little brief overview of what we're going to be talking about, there was a video that came out about 2 weeks ago. And by the way, make sure that you can hear me properly. We had some technical issues on the audios. So if you guys can't hear me, let me know. That's why we're a little bit late. So I do apologize. But let me introduce the guests first, because it's kind of amazing that they have dedicated their time to coming on my channel to talk about this. But I have two amazing guests that I would consider to be part of the leading experts on this particular topic. I have Dr. Kevin Henke. He was an American geochemist from the University. Actually, I think you're a former professor for the University of Kentucky, correct?
I was part-time, yeah, and temporary, but I mostly did research.
Awesome.
At the University of Kentucky. My PhD is from the University of North Dakota.
And it specializes in geology and geochemistry, correct?
Geology, yes. And then my postdoc was in the chemistry department.
And I also have Dr. Gary Loechelt, who is a materials science expert and solid state physics, I guess, from University of Arizona.
Well, that's where I got my PhD. Yes, from Arizona State University. Arizona State, actually.
And this has basically been something that both of you gentlemen have done extensive work on. I mean, like when I say I think you guys are probably the two leading experts on this particular topic, I think that it probably would be, at least as far as the helium diffusion rates, as far as the creationists have been trying to use them to try to give evidence for a young Earth. So to kind of dive into this, I know you guys can't hear the video, but you've watched it before. There's only 4 minutes worth of this video. But this video was by a young YouTuber by the name Taylor K that basically asked a very technical question and only got about a 1 minute response that had no substance to it whatsoever. And I was like, man, this is a lot more complicated. And I really wanted her to get the best information available on this particular topic because, long story short, young Earth creationists over the years have tried to use anomalies or things of that nature to try to perpetuate the age of the Earth being very young. And so there's two major ways of determining the age of the Earth. There's the radiological ways using, lead dating and carbon dating. Well, Geber dating doesn't go that far back, but argon dating, potassium dating, and things of that nature, uranium, thorium, all of them indicate billions of years old. But there's a little bit of anomalies on the helium diffusion rates for the atomic clocks, and this is what they latched on to say, oh, look, here, the Earth is young. So we're going to be discussing why that actually isn't the case and some of the many, many, many errors that they made in their research and their experimentations for this particular topic. Is that decent enough summation?
Yes. Mm-hmm.
Anything you want to add on that for her?
No, I think the video actually frames the question very well. So
I do as well. Obviously, Taylor's very, very intelligent, and that's one of the reasons why I wanted to do videos on this, because I think she has the potential later on to really become really strong in science. And of course, anybody who generally does eventually probably recognizes the fact that there was some errors in the younger creationist studies. So, like I said, I know you won't be able to hear her, but the outside will. So I'm going to play it for like 3 minutes so she gets to ask the question. Okay.
Hello, YouTube viewers! Welcome back to your favorite channel. So, some of you guys know that in addition of doing gymnastics videos and playing with my guinea pigs, I also like asking evolutionists tough questions on what they believe. So here are some questions and the responses I asked on the Standing for Truth channel. So, let's go.
Question comes in from Taylor K. And this question is for Mark. If the Earth is really billions of years old, why is there still helium found in rocks, given the current rate at that it leaks into the atmosphere?
Why we still have helium, because it's been created by radioactive decay. Very, very slowly, I might add.
Okay, so what Mark Reed is saying here is that as these radioactive isotopes decay, they produce helium molecules. That may happen, but is that really enough to account for billions of years? Let's see what T-Rock has to say about this.
Yeah, that's a great question. Again, it's super easy to go down these very long rabbit trails. But this is a really interesting one because there should not be helium in those rocks, period, if the Earth is 4.5 billion years old. And the reason is because helium, being an inert gas and being very, very small, will slip through crystal lattice structure quite easily. And more specifically, it's temperature dependent. So the answer Mark gave is not actually an answer. It's yes, we know there's radioactive decay. We know that the decay rate is slow. The problem is that the escape rate of helium at the given temperatures are much faster than the rate of radioactive decay of the uranium. If it's faster, that means it cannot accumulate.
Just totally off topic.
Steve, we cannot hear you either now.
Yeah, we've lost your sound here. I can hear you, Gary. Can you hear me?
Okay. How about that? All right.
Okay. Yeah.
So I think they were unable to see the video, but they heard the video, so that's fine. Again, I had to do this a completely different way because it's just the way it kind of worked out. We were trying to use meets, but we had some issues with it. But I'll get that part situated. So again, the question was this though: if the Earth is really billions of years old, why is there still helium found in rocks, given the current rate at which it leaks into the atmosphere? Who wants to just try to jump into this and kind of help answer the question for her? Okay.
See if I can start. So the claim is that rocks cannot retain large quantities of helium for billions of years or millions of years. And I would ask, says who? So one of the things as a scientist is whenever you hear claims, trace it back, because this claim has been repeated many places. You find it on websites, you find it in these videos and things like that. But you have to ask yourself, where does it come from? And in the scientific world, the authoritative source of information is usually found in the technical journals, in conferences, sometimes in textbooks. So in this particular case, all of these claims are really based upon one paper, primarily, that was published by Russell Humphreys and some of his young Earth creationist colleagues in a journal called,
Journal of Creation, wasn't it?
Journal, Creation Research, Creation Research Society Quarterly.
Yeah, that's what.
Back in 2004. So all of these claims, we have to realize they've been circulated and repeated many times, really are based upon primarily one paper. Some other work was published, but it's primarily one paper. And so then you ask, well, what was done in this paper? In this paper, there was a couple of experiments. One was, there was this deep well that was drilled in the state of New Mexico by it was near a volcano, a fairly recently active volcano. And from this well, they extracted some rock samples at various depths. And typically when you drill into the earth, you will find that temperature increases as you get deeper. And same is true, you found that there. So what they did is they extracted these crystals called zircons, and from them they measured the helium content. And what they found was at the shallower depths, where it was cooler, there was a substantial amount of helium. And as you went deeper and it was hotter, the crystal had less ability to retain any helium until you got towards the bottom where there's practically none left. So, okay, so here's one piece of data. We have a well, we have rock samples, we can extract zircon crystals, and we can measure the helium content. And we can see that it follows the trend, that you have more helium at the top, less at the bottom. So then the researchers raised the question, is it possible that if these rocks are, let's say, a billion years old, the formation was Precambrian, some of the inclusions are dated at 1.4 billion years. So let's just use that as a starting point. So the question they posed, the authors of this paper, is, can these crystals retain helium for 1.4 billion years? And that's a good question to ask. And that's a reasonable question to ask.
It is, absolutely. And when we have the age of the Earth by different metrics, they should be a consilience, right? There shouldn't be anything that says, okay, by using one standard of science, one metric, it's 4.5 billion years old, but by another, it's 7,000. There shouldn't be any outliers like that diverge from our understandable data points, and that's, I think, one of the biggest things that I would like Taylor to try to understand is that this is science, and science is objective. Being an objective, it should be anybody can go look at this data and come up with the same conclusions, right? It shouldn't be creationist versus Christian. It should be Christian versus atheist. This is science. What's the data, and what explains the data? Correct?
Right.
And
that's good. And what's also important is to understand, and I'll get to this in a minute, you have data, then you can have models, and then you can have interpretation. Okay. The data is, in a sense, the most objective part, right? I mean, if you measure the helium content of a zircon crystal at a certain depth, at a certain temperature, assuming you measured the depth correctly, the temperature correctly, and you can measure the amount of helium, that's data. Okay. In and of itself, it says nothing about the age of the Earth. All it says is how much helium you had in this particular crystal. That's what you know. You know the depth, you know the temperature, you know the amount of helium. Okay. So that is the starting point. But the question, then you have the question, because it is very true that there's a mechanism called diffusion, which is basically atoms are in motion, and when they're in motion, things can move around. And as you increase the temperature, things will move faster. And for something like helium, it can move more quickly through materials because it's a small atom than other elements. So it's a reasonable question to ask, can these crystals really retain helium? Or let's throw out the age of the Earth question altogether. Let's just say, how long can zircon crystals hold helium, without having any preconceived notion of age of anything? So you need more data. Just from all we have right now is a well in New Mexico. We have rock samples at different depths. We have, we know the temperature, we know the depth, we know how much helium's in these samples. That's all we know.
Yeah, and we should know that why should we find helium to begin with? If you want to explain to people maybe why an alpha particle exists as far as like the uranium decay chain, why do they have this problem of missing radioactivity? This is the whole thing that rates, which was the radioactive and the age of the Earth program, kind of wanted to determine why is there missing radioactivity and heat. How much heat's going to be involved if we have to account for this much radiation from decay all the way down from thorium to lead, which produces these alpha particles, which are just ionized helium, right? So they're basically arguing if the age of the Earth is 7,000 years old and we have all this helium, it posits something called accelerated decay as a mechanism to explain why there's more helium in there than what there should be, according to them, correct?
Yeah, and that's true, and that's a good point. And something else, whenever you have some of these disagreements in science, what's helpful sometimes is to not just look at the disagreement, but look at the agreement. So these younger scientists basically agree that this helium came from nuclear decay. They agree that the radioactive decay produces helium, and given the amount of helium, it took tremendous amount of nuclear decay, which is what the mainstream scientific world would say. So the only difference there is the young Earth creationists believe this decay happened over a very compressed period of time, and hence that's accelerated nuclear decay, and that's their whole theory. But in a sense, they agree that the source of this helium was radioactive decay, and it took a lot of radioactive decay for that to happen. And if it happened at the rate that we observe today, the Earth indeed would be billions of years old. They concede that. I even use this phrase, so much helium, this would be billions of years worth of radioactive decay at current rates. They even use this phrase over and over, which is conceding that quantity-wise, it is billions of worth of decay at today's rates. Now, they take the further step saying, but we believe nuclear decay rates were accelerated. But regardless, both sides agree that this helium came from nuclear decay, and there was a lot. So that's
I think it's an exceptional point to point out is that the creationist model, the creationists themselves have agreed that the data is correct. They have agreed that there is a lot of radiation to be accounted for. There is a lot of radiological decay. Everybody agrees on that part of it, right? Everybody's just on the same page. There's no discrepancies on that. There's no even maybe at one time maybe creationists may have denied that, but as of I would say at least the last decades.
There are a number of young Earth creationist critics of Humphreys that go for more chemical explanations, and that would be like Carl Freud and Jerry Ackridge. A number of
they diverge on that.
Humphreys has a number of young Earth creationists that disagree with him.
That's odd because it's still, I mean, they still have to have. They know radiological chains work. They know that the decay chain is the decay chain. They know how, in theory, how long it takes for things to decay and what particles being produced. Most creationists I've talked to, none of them have an issue with that. It's always, okay, we accept all this, but let's explain it, and we explain it by an accelerated decay process, and that presents the problem with, okay, if that's the case, then how much heat's going to be produced here? A lot.
You see that, Andrew Snelling actually looked at meteorites back in 2015, and he said their uranium lead is not due to accelerated radioactive decay. He thinks that God just zapped it.
Yeah, there's a
in those ratios that way.
Yeah,
that's how he explains the chemistry of meteorites. And again, Freud and Ackridge disagree with Humphreys and argue that there's other causes. I think Woodmarap also looks more at chemical explanations for isotopes rather than accelerated radioactive decay, although I'm not sure with Woodmarap.
Would both of you agree, though, that first of all, there's no signs it's a chemical type thing. It's radiological decay has been well established as far as physics. But this is something, if you guys remember Gentry's work when he was working on polonium halos, eventually he even had to concede something very similar to what you had said. He said, this was called a singularity, a one-time event where God just made it this way because the science didn't work in his favor. And again, once you have to do that, you lose all objectivity. If you have to say God did it this way in order to promote your scientific theory, you're no longer in the realm of science. And this is why I deal with a lot of Christians from reasons to believe where they don't do any of that. They avoid that kind of stuff. They're like, okay, if God exists and God created the earth and the earth is billions of years old, which they do accept, how do we explain it scientifically and using scientific modeling? And I do respect that, because once you say, like Snelling would say, God just did these ratios this way, would you guys both agree you're no longer in the realm of science?
Yeah, you cannot falsify that as a hypothesis.
Yeah, it's unfalsifiable. It's
the scientific hypothesis.
It's ad hoc.
Is that it's falsifiable, that you could find evidence against it. And when you appear to arbitrary miracles, you do step outside the realm of science. I mean, you could call it philosophy or some other branch of thinking, but it's not science, because how do you falsify an event like that? Because if I bring contrary data to the table, you can always come back, well, there's yet another miracle to account for it.
Right.
Like the classic example of what we're talking about now, the accelerated nuclear decay. If you really compress a billion worth of radioactive decay into 1 year, it'll generate so much heat to melt the earth. Okay. Well,
and they agree with that. The creationists agree with that. They know they have a heat problem.
To invoke a second event that somehow the heat had to be taken.
God dissipated the heat by miracle, heat radiation by putting on,
And so it never
cooling
ends.
fans.
You can never come to the end, because whenever a contrary piece of information is put to the table, you can always invoke another miracle.
Yeah.
You say, well, no,
that's a God hypothesis.
He can do anything, but if you take that point of view, you can prove nothing.
Right, and I think it's, again, if you start having these ad hoc positions where, again, the rates program did acknowledge they have a massive heat problem. I mean, if you read creation.com, they acknowledge this as a massive issue with young creationism. So they recognize this. They don't try to at least sweep that under the rug. Unfortunately, their hypotheses to overcome that, again, we don't stay in the realm of science when they start positing God put holy cooling fans on the earth. It just makes no sense. So to kind of like catch people up on the speed on this, Dr. Humphreys, who has been writing a lot about this, wrote to you specifically, Dr. Loechelt, on this particular topic, and it was from the Creationist Research Society in 2018. You mentioned that. I have it right here that I'm pulling it up.
Yeah.
If I don't know if Kevin wants to pull that up, or he wants to put on his Talk Origin site, he also talked about these particular topics and what mistakes they were making in their evaluation of why they came up with the conclusion that there's too much helium in there.
Yeah. Okay. If it's fine with you, I'd like to talk about now the laboratory experiment, because that's like the second piece of the puzzle.
Yes.
So we've covered the first. There's two puzzle pieces to understand this problem. The first puzzle piece is you have this well, drill into the ground, and then you extract samples at different depths. You know the temperature, you know the depth, and you can measure the helium content. And so what you know is this sample at a certain depth, temperature today, which might have been different in the past, has a certain amount of helium. Now the question that's being posed is, how long can helium stay in these crystals? So to answer that, Humphreys, and in fact, other researchers, I shouldn't just research them, they use laboratory experiments. And let me talk a little bit about the laboratory experiment and how that relates to the question, because the question is, we can observe the helium, we can know the temperature, but how do we know how long the crystal can really hold that helium? So they perform a laboratory experiment, and it goes something like this. You take the rock sample, you crush it, you extract these zircon crystals. So already you've taken them somewhat out of their natural environment. You put them in a vacuum. So that's
it's not done in situ, obviously, right? Yeah, you have to take them out and cook them. Yeah.
Yeah, and then in this vacuum chamber, you can control the temperature and time. You can heat it up and cool it down, pretty much as you will. And as you heat it up and cool it down, you measure how much helium is released. And over time, you get some idea of the helium retention ability of the material. And since helium is lost by a mechanism called diffusion, there is a quantity that sort of measures how fast diffusion occurs, and it's called diffusivity. Okay, so these experiments measure diffusivity. So now you have a fundamental problem, and this is an important thing to really understand. We're trying to understand how long can these zircon crystals retain their helium over time. We take them out into this, in a sense, laboratory environment, a very different environment, and you heat it and cool it, and it goes through a regime that's very different from what it saw in the field. And you're observing gas release over a period of maybe a couple days. A lot of these experiments, they step the temperature up and down and maybe repeat that a couple times. And when they do that, maybe they hold it at a certain temperature for an hour or two. And if you have 20-some steps in this, you're observing things for a couple days. So now you have a second piece of information. I've observed how under these laboratory conditions, which are very different than the field conditions, how it retains and releases helium over time, over a couple of days. But now the problem is, I've only observed the system over a couple of days. How can I infer what's happened over the course? What would have happened over the course of a year, or 1,000 years, or 1,000,000 years, or 1,000,000,000 years? You see, I have a very, very narrow time window of observation of this system, and I'm going to try and infer what that means over a longer period.
You have to extrapolate, clearly.
Well, you have to have a model, and see, this is important. And this is a key part that I think is very much neglected by the work of Humphreys. And that is, the only way you can really bridge this gap is you have to have a model. Okay, you can't just extrapolate. in a sense. You can't just rely upon statistical and empirical means to extrapolate over many orders of magnitude. You have to have underlying this a model, and that model has to have a solid theoretical understanding of the material. And if you don't have a good model, your extrapolation can have huge errors because you are extrapolating in time a factor of over 1 million, even for 1,000 years. Think about it. To go from 2 days to 2,000 years is 5 orders of magnitude.
Yeah, it's
right.
100,000 years.
100 days
100,000
factor.
Yeah, exactly.
And then
factor
multiply
100,000
by 1,000. So now you're looking at 100,000 just to get to 1,000 years. So you're going from a very narrow time window of observation to a very long extrapolation, and you do that by means of a model. And whether it's correct or not depends a lot on the assumptions of the model. So I think this frames the problem, I think, appropriately.
Yeah, and I absolutely think that modeling would be the way to go. Now, I remember quite specifically that the modeling that they used was a very, very, I guess, lack of a better word, naive model that wasn't requiring. They didn't require any kind of like advanced modeling, which should have been used. And if you don't use the right modeling, as you said, you get the wrong answers. And your modeling, which is your field of expertise, takes into account all these things and magically seems to be, if you use the correct modeling, it comports with what we already know about the age of the Earth if things are done properly. It's when you don't use the right modeling, then you get these weird anomalies. I mean, a factor of 100,000, that's a lot. That's a huge discrepancy. That's a 5 orders of magnitude is not an insignificant, trivial difference.
Yeah. So that's a good point. That's sort of where I come in, because when I originally read this study, I was a little bit skeptical. But in my background, I have both a nuclear physics background from my undergraduate days. I worked at a facility in Washington called the Hanford Reservation, the Hanford Nuclear Reservation. And for those who may not have heard of it, it actually has a very famous history, or maybe infamous history, because that site was started back in World War II. It was part of the original Manhattan Project, and their mission was to produce plutonium that was eventually used for the second atomic bomb. So it was a place that has, basically nuclear expertise since the earliest days and when that was being discovered. So I had experience there. And then once I got into graduate school, I transitioned from nuclear physics into material science. And going into the semiconductor industry, one of the things, and people may not realize this, that for all the electronics that are around us, I mean, there's more transistors on this earth than people by a huge margin, okay? But these transistors, to build them, you have to add chemical impurities, and then you have to heat them, and then you have to, and that's diffusion. So our industry relies upon having very, very accurate diffusion models for any of these devices to work.
In other words, if the modeling didn't work, the devices wouldn't work. The devices that use transistors on solid state physics and any kind of CPU, it's not going to work right.
Oh yeah, and experimentally, we've seen experiments fail because we didn't fully understand the diffusion, and a certain profile went too deep or too shallow, and things like that. So, where was I going? So I was kind of skeptical, but I one of the things, and this is something else I really want to emphasize. It's one thing to be skeptical, but I think we should always try to listen to one another, because I see this on both sides, young earth creationists and on the secular side, that people will dismiss something that doesn't fit their belief paradigm without listening to the other party. And it's important, I think, even if you disagree with people, to try and listen to them and give them a forum. And Steve, I think that's where you've done a great service, I'd say, to the intellectual community by being willing to even go as far as flat earth people and things like that. It's like, hey, we may disagree with it, you may be completely wrong, but you deserve at least a forum in the community.
I appreciate that. And it's made a difference, because there are people that have left flat earth. There's people that have left young creationism. I had a gentleman named Wayne Philmore that I did a debate on macroevolution. And he left younger creationism after that. Like a month afterwards, he realized that I was correct on it, and that yes, the macro evolution is a legit thing. And so I want people to have a repository of sorts where they can go to and look at these things to find out for themselves when they have these types of questions. Now, I have links in the video description of all your gentlemen's work, and so when Taylor, has a chance, she can go through and kind of review, read these things, right? But can we kind of maybe start with the modeling and some of the mistakes that they made in their modeling? Because I think that's really the crux of it. Is why is it they got the results they got? Why is it that they have such a skewed divergence from mainstream modeling and some of the mainstream work that has been done in this particular field that I think has been pretty standard. I mean, it's just this is ubiquitous in science, but they're getting these really radical differences. Why is that? What's some of the things that they did wrong?
I'll focus on two, which were really the big ones. And one is, and I think in Taylor's video, this was mentioned by the younger creationists, saying diffusion is very sensitive to temperature. And that's very true. It is exponentially sensitive to temperature. So if we're going to model the retention of these zircon samples from this well in New Mexico, it's good to have a temperature model. Two things. You need to have a realistic temperature model of history, and you have to have a model that can incorporate changing temperature. So Humphreys made a very, very big simplification. He said, and I think it's partly because he didn't have a model capable of handling temperature changes. So because he had a simple model that did not handle temperature changes, he basically took the temperature that's measured today and said, well, can these zircon samples retain helium for 1.4 billion years at this temperature? And the answer is no. And I agree with him. The answer is no. This is a point of agreement, not disagreement, that at today's temperatures, these zircon samples could not retain helium for 1.4 billion years. But my point of contention is, who says the temperature at this site has been constant for 1.4 billion years?
Yeah, they assume
they
assume a uniformitarianism. They assume a constant temperature.
Yeah.
Do they not? They assume.
I've got a graph here of Gary's graph showing this. Did you want?
Good.
Yeah, there it is.
Yeah, thank you.
This is the Humphreys model, and this is Gary's realistic model here in blue, showing that from the geology of the site, the temperature has varied at this location at Fenton Hill a lot over the past billion years. And particularly, it's gone up a lot recently from volcanism in the area. And it's now hotter than it has been since about 800 million years ago, according to uniformitarian standards. So this was definitely a mistake from Humphreys' point of view, assuming a constant temperature.
Thanks, Kevin. This tells the story well. And if you look at where that temperature starts to bottom out, let's say, around 50 degrees centigrade or so. One of the things to remember, or the background behind the story, is why were these wells drilled in the first place? Well, it was part of a geothermal energy program by the Department of Energy. And the reason they drilled these wells next to this volcano is because the rock was extremely hot. It was extremely hot because of the volcanic activity. And it's not what you would find in your backyard unless you lived in Yellowstone or something. These are extremely unusually hot rocks. And see, this is the thing. The volcano, by conventional geological estimates, erupted about 1 million years ago. And subsequent to that, there were additional eruptions as recent as best we can tell, 40 to 60,000 years ago, which, as Kevin, to a geologist, 40,000 years is a blink of an eye. I mean, that's hardly an eyelash on your eye. And these samples, the bedrock, the Precambrian rock, is dated at 1.4 billion years and older. So think about it. To take even the event of this volcanic eruption a million years ago, put that in the context of 1.4 billion years. So you're basically throwing away 1.3991 or 999 billion years worth of history just by taking constant temperature today and extrapolating that back.
Well, they have they don't believe those those billions of years, so they just kind of toss them to the side. Which, when they don't include it, then you end up with something like a mistake like this, where you're going to. There's no reason to assume constant temperature by any means over 40,000 years. Even I think even 40,000, but for 1.8 billion years, there's no possible way you have that kind of constant temperature. Correct?
No, absolutely. And in fact, if the temperature at that site really was constant for that long, it would require a tremendous heat source. And that heat source would have pretty much heated the entire southwest of the United States, because heat, like helium, diffuses. And so we know by the extent of the heat around this volcano, it hasn't been that hot for that long. It can't be. Some of the surface wells they measured there, they saw some of the heat change even over the course of the study, even the course of decades. So this site is being very actively heated today. Mm-hmm. There's evidence that because of the hydrothermal, which just means the hot water that's flowing in the rocks underground, it's very geologically active, thermally active. And so in such a dynamic system, to not take into account temperature dependence is absurd. I would say absurd. You can't just take one temperature point and extrapolate that back 1.4 billion years and say that's your model.
Yeah.
You have to make a realistic attempt to follow the history, because, and see, this is the thing. If these rocks really are 1.4 billion years old, they have a huge history. They've seen at least 2 supercontinents come and go. They've seen seas come and go. They've seen volcanoes come and go. And you have to take all those things into account if you're going to model accurately. And just to give an example, I'm kind of sensitive to this issue because this is my work. I do diffusion modeling as part of my routine job. And if I was asked for one of our semiconductor wafer fabs to put together a diffusion model for a certain process step, the very first thing I would do is I would contact the process engineer in the factory and say, give me the temperature profile of your recipe, because I'm not going to put into my simulation a diffusion model until I know what your temperature. Give me your ramp rate, give me your hold time, give me your gas flow, give me all that information. And to me, this is routine. In other words, I don't put together models for my work without asking the question, what was the temperature history? And so this is the first thing I latched on to. It's like, you can't just take one temperature and extrapolate that in time. You need to look at the variation over time. And when you study, you realize it's cooler throughout much of the recent history, which is not a surprise, because they selected the site specifically because it was unusually hot.
Well, let's talk about it for a second. We had a super chat. Lady Firebrand for $2 Australia says, very much enjoying this and hope to see more. I appreciate it. I look, for the last year, I did a lot of philosophy stuff. So I really wanted to kind of get back to some sciencey stuff. I do have Dr. Hugh Ross coming on to talk about the starlight problem. I think, Gary, you've worked with him before, if I'm not mistaken. At least you know Dr. Ross.
They've been a supporter of my work at some level. I mean, I'm not huge at RTB, but
you have name recognition there. I assure you, you have name recognition there.
Yeah, I was on one of their podcast lists. That's probably my biggest accomplishment there. Okay, so can I move on to the second major?
Yes, absolutely. Yes. So before we get to the second major thing, by the way, should we also note, even though it's, I don't know the huge ramifications, but just so the audience knows, one of the errors they did make is they misidentified the rocks. Correct? I mean, because he made up. I remember the name. I don't remember the name that Humphreys came up with. He pulled some name. He just created
granodiorite.
Granodiorite. Yet, but it was actually gneiss. Correct?
It's
nice episode. Yeah, nice. It was nice.
And that's a very important distinction. Granites, granodiorites are igneous rocks. They form from melts. In other words, you get magma deep within the earth cooling to granites and granodiorites. Granodiorites have more magnesium and iron and less silicon in them than granites. Now, a gneiss is a baked igneous or metamorphic rock. In other words, you have a rock, like maybe a sedimentary rock, like sediments, or you could have a granite, and it gets reheated, and but not to the point of melting. Under either, it could be under high temperature and or high pressure. And this causes different minerals to form. Now, what's complex about it is that let's say that you have a gneiss that was once a group of sediments. Okay, you look like sediments at the Mississippi River Delta. It brings down zircons. Zircons are not soluble in water, and they're very tough and hard. And so you can have zircons washed down from the Rockies and into Louisiana. You can have, and they're usually around 100 million years old. And then you get zircons from the headwaters of the Mississippi River in Minnesota. They're 2.5 to 3.5 billion years old. And then you can get zircons coming down from the Appalachians through the Ohio River that are, 250, 600 million years old. And you get all these zircons mixed together in these sediments. And potentially then they get deeply buried and metamorphosed. And under metamorphism, you can grow more zircons. And so you end up with these different family of zircons at different ages. And Humphreys and Wright failed to realize that when they sampled these zircons, they could be radically different chemistry. And Gentry actually published a paper in 1982 in Geophysical Research Letters, where he listed the uranium and the thorium and the lead concentrations of zircons. And some zircons, even on the same zircon, you got uranium concentrations varying by an order of magnitude. And Humphreys completely ignored that.
Yeah, I think it's pretty significant when they misidentify rocks. And if I'm not correct, correct me if I'm wrong, but I think they identified literally, I'm not even exaggerating here. They said, oh, it looks like this, therefore it's this.
Yeah, that's what Baumgartner did. He
Yeah.
looked at it, looked at the color of the grains. The problem is that different minerals can have different colors, or I should say the same mineral can have very different colors. Calcite, for example, can be black or blue or white or pink. Same thing with quartz. And then, so you can't go by color. You have to actually analyze the chemistry. And Baumgartner didn't do that. Now, to his credit, apparently Baumgartner later admitted that these rocks were gneiss.
Yeah, I think they did correct that. That's one of the few things that I saw they did put a correction on.
Yes, yes. And so, but that has huge ramifications in their models, because they don't know where these zircons exactly came from. If they're metamorphic, igneous, they know that they're 1.5 billion years old or so from the uranium lead dates. But again, if you look at Gentry's paper, the uranium and lead concentrations radically vary from zircon to zircon, sometimes within the same zircon.
Yeah, and I think that's something that needed to come out, to be talked about, only because this is again something they've recognized they made a mistake on. So in helping to answer Taylor's question, these are things that objectively have already been happening. These things they've already been brought up. They did recognize they've made certain mistakes. They haven't corrected other mistakes. Although I do have an email from Dr. Humphreys, which I'll show, because he not only did he say by all means make my emails public, he actually was advocating for it. Like, yeah, please do. So I do have him admitting that he did make another error, which we'll get into. But Gary, go ahead and finish from the temperature, the modeling.
Yeah.
Because I think that's just a huge significant issue that they got the modeling wrong, and Humphreys unfortunately made some math mistakes.
Yeah, and since diffusion exponentially depends upon temperature, if you look at some of the temperature differences between the time-dependent history and the constant history, it's huge. I mean, over 100 degrees. Is
that for both the high temp and the low temp line, or just the high temp where heat is dominant? or in the low
Well,
the low
okay,
temp is activation
this
energy
is
more dominant.
this is the field part of the study, not the
Yeah,
laboratory
analysis.
part. Yeah, the laboratory is separate from this.
Okay.
We're talking about the field part now. Okay, so this modeling error is probably the easier one to understand, right? Was the temperature constant or did it vary? The second one is in fact even more serious than this, but it's more subtle, so it's a little bit harder to explain. But I'll do my best. And Kevin or Steve, if you can find one of my diagrams that showed the crystal lattice with the dislocation and then the helium atoms. I don't know if you have that somewhere.
Which one's that one? I got a lot of stuff here.
If one of you can find it, but I'll keep talking while they start looking for it.
Let me see. You mean something like
this?
this?
Will work. Yeah, that will work.
Okay.
So, well, that's a good picture. So here's the thing. In Humphrey's model, he treated all heliums as if they behaved the same. Now, if you were dealing with a gas in a vacuum, that might be reasonable because, I mean, helium atoms are the same. Helium-4 is helium-4. But that's not true in solid-state diffusion because, by definition, you're diffusing in a solid, and the interaction with the surrounding atoms becomes very, very important. And so when you treat all atoms as if they behave the same, you're missing the fact that, like this diagram shows, it's just very schematic, but you get the concept. You have a crystal, which by definition means you have a regular array of atoms. And then you have these impurities, in this case, the helium, in different spots. But crystals are not perfect, and especially ones that are grown natural, that just naturally occur. There's defects of all sorts and kinds, and that will be present. And you can just kind of see conceptually from this picture that if you have one of these red atoms that's in a lattice plate surrounded by a bunch of neighboring atoms in the crystal, it's like a cage. It's kind of trapped there. But it's possible for some of the atoms to be in a defect site or something, which will have a very different environment. And it's not hard to visualize that once these atoms start moving as you heat it up, those green atoms can probably move a little bit more easily than the red atoms.
So the interstitial hydrogen.
You have to take into account that that atoms in different states in a solid will behave differently. You have to treat them as separate populations when you model them. Steve, you had a comment?
Yeah. So the green interstitial helium atoms, when they start getting higher temperatures and they start getting more energy put in that system, that overcomes any kind of loose bonding, and that will go through these defects, these fracture defects, and escape into the atmosphere. Correct?
Yeah. So what will happen is the green atoms will escape more quickly than the red atoms. So let's talk a little bit about the diffusion experiment from Humphreys. And Kevin, if you can find one of the graphs with the slope, the two slope, that might be helpful.
Like this one?
Yeah, I guess that would work. Yeah.
Well, I could give you another one, but
yeah, I can talk to this. So if you look at the data points there, oh yeah, that's a good one. So you have there okay, let's talk about what was measured in the experiment, because the red squares and the purple ones are the models. But let's just talk about the measured laboratory data. So that would be the little blue symbols, the blue diamonds and the green diamonds. And if you notice, most of the data at the higher temperature falls along that blue line. I mean, there's quite a bit of data there. I think like 15 or more data points. Mm-hmm. And if you notice, it follows a certain trend of a fairly steep slope of a line. And that's an indication of a atom that's more tightly bound, because the theory behind this, and like I said, you need to have a solid theoretical understanding to make reasonable models. The theoretical interpretation is that those atoms are more tightly bound inside the solid and they're harder to move. So they don't start moving until you go up to the higher temperatures. And conversely, if you go down to lower temperatures, they essentially freeze out in the lattice. I mean, they get so cold that by the time you get down to more 200 degrees and below, they're essentially frozen. I mean, that diffusivity is so small that they're basically mobile. They're very much trapped. But if you notice, there's these 4 green points. And these 4 green points fall on a very different curve. And it has a much shallower slope. And if you look at the creation model, they're relying entirely upon those 4 data points. The rest of the data does not support their hypothesis. And if you extrapolate that high temperature data down to lower temperatures, it is actually closer to the old Earth, or in this case, they call it the uniformitarian model, than their creation model. So the high temperature data is telling a story that there's a lot of helium that's tightly bound in this crystal, and that only a small percentage of it has this lower slope behavior, which is more loosely bound. And that is but it's those 4 points that they're using to justify their model and say, hey, we got this good agreement to these 4 data points, ignoring the rest of the experiment. Now, just from a data number, I mean, 4 data points versus 15, you're excluding a lot of the data. What's not apparent in this graph is how much helium is contained in those 4 data points. It's 8 parts per million. In other words, 99.9992% of the helium was released in the high temperature part of the curve. Only 0.0008% was released in those 4 data points. In other words, you're talking about a very, very small quantity of helium that demonstrates this more loosely bound behavior, which is what you'd expect if the majority of the helium was in these tightly bound lattice sites, and a small fraction was contained in these loosely bound sites.
Now,
one of the big things I did in this model is I separate these 2 populations, which is the way in my industry, that's how we handle this problem all the time. We encounter this problem on every element we look at in diffusion. We have multiple different populations, and we have different diffusion models for each one, and then you sum them up at the end.
So those 4 data points seem to be
as one single. Basically, he treated all helium atoms as the same. And I said, no, you have to respect the different populations and where they come from in the crystal.
Okay, so those 4 green data points, which look like they're in the knee there between the 2 slopes. You have the low temperature slope, you have the high temperature slope. Yeah. All those different domains require a very specific type of modeling. What they did, you're saying, is they took those 4 data points in that intermediate region between the high temperature and low region, and they just didn't care about the proper modeling to be used, and said, okay, we're just going to go with a very simple approach and say that this is going to be extrapolated all the way down from the high temperature region to the low temperature.
Yeah, basically they're claiming that practically all the helium in the sample behaves like those 4 data points.
Which makes no sense. They're throwing away all the other data points.
I think it makes no sense. It's totally contrary to everything that I've learned about diffusion over my 25 plus year career. I mean, in the first days of my internship at Motorola, I worked with a guy who was a process expert in diffusion, things like this. And some of the basic things I learned in my very first summer there was how that diffusion is not a simple thing when it comes to solid state. You have to look at different states that could exist in a solid, and each solid crystal is unique in terms of the different states that this atom can occupy, and you have to respect the fact that if you have an impurity, in this case helium, it can be in any one of those different states. Each one will behave differently, and you need different models for each one.
Okay.
So that's one a little bit more subtle. But when you start talking about how can the 2 things be off by orders of magnitude, look at how those lines start to diverge. And especially as you go to lower temperatures, it gets wider and wider apart. And in fact, this is another sign. I made some other, there were some other modeling errors that were made in the rate study, but they're interesting. They were errors that didn't make the samples look younger from their point of view. They made their samples look older. Think about that.
Mm-hmm.
They made some, well, I would challenge some errors in the modeling that made their samples look older. Think about that. So so I took their model, for instance, you know, a couple things that affect diffusion. One is the size of your crystal. You know, the smaller crystals are going to lose helium faster than the big ones. It just takes longer to get out. That makes sense. The other one is the boundary condition. How do you treat what's around the zircon? Okay, how fast? Because once it gets to the boundary, how fast can the helium continue to leak?
Did they use the wrong model for the wrong geometric shape zircon crystals? Because it's obviously the surface area is different.
I mean, they used, the zircon tends to be a long, skinny. Kevin's going to find a picture.
Yeah, I'll find a picture of the zircon.
Yeah, they tend to be long, skinny crystals with a lot of surface
They
area.
assume
Right?
the crystals were a sphere, and of course, they're prisms. And let's see.
Yeah.
So it really helps if you're going to measure how much how much helium is being released. You really need to know what exact geometric shape you're dealing with, because different surface areas are going to have different line defects and fractures near the surface. That's going to be completely different in their model of releasing more when you have temperature, at heat.
Yeah. See, they assumed that this was a sphere.
Well, and in fact, a lot of people do. But then the question is, if you approximate that with the sphere, what dimension do you use? And if you read the literature, the best approach, if you're going to use a spherical model, the best approach is to have a sphere with the same surface to volume ratio.
Yeah. So it's really dependent on your surface area more than anything else.
Yeah.
Is that the most critical factor, the surface area?
Well, yeah, because in a sense, the volume is what contains the volume contains the helium. The surface is where it leaks.
Mm-hmm.
So if by having the same surface to volume ratio means you have the same volume containing helium, you have the same amount of surface area. So what Humphreys did is he picked the longest dimension, which actually makes the crystals hold more helium. Okay, think about that. And then the second thing, a lot of these crystals are found in another mineral called biotite. And from their studies of biotite, it shows biotite has less of a capability of retaining helium. But in their model, they assumed that around the zircon crystal was a biotite shell. And they assumed it had the same diffusivity of the zircon. So both of these things made their ages look older. Think about this. They said, our model predicts a 6,000-year-old age, but they use these approximations that make it look older. So what I did is, well, what if you take away this biotite shell, which is what I did in my model? What if you use the surface to volume ratio, which I did in my model? You would get a diffusion age of only 600 years. So if you believed their model with just these two changes, you would have to dispute whether Columbus ever found America.
So the Earth isn't billions of years old. It's not 6,000 years old. It's only 600 years old.
It's 600 years old.
So the 600. So funny is if you had people out there that advocated the Earth was 6,000 years old, they would take that data from Humphreys and then they would run with it.
Yeah.
Even though they got it wrong because the model was wrong. Yeah.
I could take the same data and come up with a more realistic boundary condition and size and argue that the Earth is only 600 years old. And I don't think anybody would buy that. And the reason I say that is, why did they make these approximations? And it goes back to that diffusivity. It is so far off that if you use their interpretation of the diffusivity, you can't even get a model to keep helium for 600 years.
Yeah.
You see the point?
Yeah.
The diffusivity that they use, the way they model the solid, is so far off that they actually have to have these band-aids, so to speak, so that you can go from a 600-year-old model to something that's at least 6,000, which is fits their expectations. So they had to put Band-Aids. The diffusivity model of the solid was that bad. They had to Band-Aid it. And when I looked at that, and I'm thinking, okay, if I'm going to demonstrate retention over billions of years, and I take away these crutches, it's going to be harder to demonstrate retention over a billion years. But I said, no, I don't care if that works against the hypothesis.
Mm-hmm.
I'm going to do the right thing. I'm going to pick the right boundary condition. I'm going to pick the right grain size, even though I know it will result in more helium loss. I'm just trying to do everything as accurately as I can without regard to the outcome. And what is amazing is when you actually put care into the details in science, and you put it all together, it came out with a realistic answer
that conforms with the old Earth model, right?
I made some approximate or model choices that actually went against trying to retain helium. So and it amazed me, but it didn't. It just shows the power of science that when you actually do things.
Yeah, and other papers that of actual scientists that have done these experiments, they come up with the same thing using the correct modeling. They all come up with an old Earth. It's not like they start with the premise. One thing about young creationism you have to remember for my audience to recall this is that they have a statement of faith that anything that goes against the young Earth creation position, any evidence that goes against it, can be discarded by them by fiat. They can just say it's wrong. They don't have to give any reasons why or anything. They believe very strongly that any evidence that goes against a young Earth is just automatically wrong, which is not how you do science. And if you took that approach, I don't think we could have anything computers wouldn't work, airplanes wouldn't fly on time. Nothing would work if we took that approach where we start with a premise and then we work or the modeling around that premise, when in reality, physics doesn't work that way. The facts remain is that the modeling that you have used in your work works. It works because it's been demonstrated to work in solid state components. Simple as that. It works. Humphrey's model wouldn't work in any of these components. That's a huge thing that I think people should take away, is that the proof is in the pudding, so to speak.
Yeah.
Oh. All right. So what was the next you going to here? Going with the depth and then the air bars, the range bars.
Yeah. Well, just showing how I guess the point here is the gray squares is again what we're trying to show is, can we match up what we measured in the field from these samples to the model we create based upon this laboratory experiment. And so the gray squares is this amount of helium remaining in the samples in the field, and the blue circles are what I predicted from my model. And the point is, within the range of the experimental error, and there was a lot of uncertainty in this data. This was not a high quality data set, and Kevin can attest to how it's hard to make any kind of reliable conclusion just because the quality of the data is so poor. But doing the best I can, this is the best I did, and it just shows when you put in all the numbers and you do things right. I got what I consider to be a reasonably good agreement to data without any special exotic physics.
Yeah, it is notable that Humphrey's modeling is so far outside the norm that everybody else got. It doesn't matter who did these samplings and the experiments. I think the Fenton Hill was done by Caltech, wasn't it? They're the diffusion part, right? Not the geological part. Yeah, exactly. And so they have, they had no skin in the game. They're going to get the data, and they're going to get the data that they get. And it's weird that you just have like one or two people that are trying to interpret the data in such a way that has to, as you said, use these far-fetched types of modeling, because again, they're trying to force fit their model to the data. I mean, they're basically saying this has to be this way. I actually had Humphreys tell me about when it came to accelerated decay, because when I was asking him, okay, what is some of the evidence for accelerated decay? And of course, this is to them evidence of accelerated decay. But the real evidence that he said was basically because it has to be. There could be no other way. That's not an answer because he's already taken the approach that the Earth is 7,000 years old. Therefore, the only ad hoc model that they have that would even remotely make that work would be something like accelerated decay, which again presents another problem, the heat problem. But it's so bizarre that you have such an ad hoc way of doing things rather than just go, okay, why don't we just look at the modeling the way everybody else recognizes it to work and what you did, and oh look, they're right. Look how perfectly they're in the range.
Yeah, and since you mentioned everyone else, should we talk about Wolfenstock now?
Yeah, we can talk about Wolfenstock. I thought I had that paper here, but I can't seem to find it. I have other papers that I brought up, but I didn't get Wolfenstock. But that's okay. You could talk about it.
Yeah. So Wolfenstock. So one of the principles of science is that that scientific fact is established by verifiable, reproducible data, meaning you don't trust one-off experiments. You try and find ways of reproducing a result. And keep in mind what the basic experiment is. It has two pieces. It has a field study where you have a well and you take samples at different depths and you measure the helium and the temperature. Then the second part of the study is you want to measure the rate at which these zircons lose helium. So you take these crystals, you put them in a vacuum chamber, you heat that up, cool it down, heat that up, cool it down, measuring the gas release each time. You build a model for the diffusion in that, and then you apply that model to what you observe in the field. Mm-hmm. Well, it turns out two scientists by the name of Wolf and Stockley, and again, to point out, both of those are Christians. I met Melissa Wolf, dear Christian gal, and I think she mentioned, I may be wrong, but I think she mentioned that Danny Stockley was Catholic. So, two religious people. And so one of the other things I think I want to point out, and Steve, you as well, this artificial dichotomy, is it creation, is it evolution? There's a spectrum in between. There are people like me who do not believe or believe in a God, skeptical of Darwinian evolution, but yet accept an old Earth and an old universe.
Yeah, there's no one size fits all. That's for absolute sure. Yeah.
Well, so it's not this dichotomy. And as a Christian, this perhaps grieves me the most, this label that if you don't believe, it's almost like if you don't believe in a 6,000-year-old Earth, you don't believe in the Bible, and you don't believe in God, you might as well just be an atheist. And I've actually read writings from young Earth creationists that basically almost told me that why even bother being a Christian if you don't believe in a certain calendar date of creation?
Yeah, that's a great point.
My response is there's a lot more to being a Christian than calendar date of creation, especially since that wasn't even codified until really Usher, and that was only within the last 500-600 years. In other words, that's not something that's even part of historical Christianity.
Usher's chronology was pretty recent in his determination to reach that number for 6,000 or 7,000. But you made a great point because, like for example, like I have a great respect for Dr. Ross. I don't agree with him on a lot of things, because I am a secularist and I'm not a believer. But the science is science, and it doesn't matter whether you're a Christian or not. But when it comes to the science, and I think it's interesting to note that here you have Dr. Humphreys and Snellings and Bumgarner, who are Christians who advocate for a young Earth. But on the opposite side, you have yourself, who's a Christian, Dr. Ross, and many other people that I know, Dr. Fazrana, advocating that the Earth is very old. And yet all of you are Christians. So it's not a matter of, it's the mean atheist or it's the mean evolutionist that's promoting these types of things, explaining, like this type of subject. This is science. This is science. And science doesn't care what your religious affiliation is. It's either the data is right, the data is wrong, the modeling is right, or the modeling is wrong. There isn't any factor that needs to be weighed in, whether you believe in God or not, for the science. And that's one thing I really want Taylor to take away from, is that why is it you have all this, you have a handful, a small group of religious people that are PhDs and doctorates that are trying to, in my opinion, manipulate the data and get many, 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 many things wrong. And then you have a more mainstream, you have a lot of them, Christian PhDs, yourself, Dr. Sye who does accept, Darwinian evolution, or at least modern evolution synthesis, And they take a radically different approach from the younger creationists. They're like, well, here's the science. The science says this, and they base their beliefs for Christianity around that, because I think the science is a lot more objective. So they can't just say that this is some kind of an atheist thing at all. This is independent of theological beliefs. Would you agree on that? Because I think that's a huge takeaway. Because a lot of people I see in the younger creationist community, they're like, oh well, a younger creationist who has a PhD is telling me this. Well, yeah, but what about the PhDs who are old earthers, who actually know the science better?
Yeah, and I just want to make that point because so often I feel like I get stereotyped by the younger creation crowd because I disagree on one doctrinal point and not looking at the other things of the Christian faith that I think are more essential. So that's just a little background. But this is the Wolf and Stockley study. So conceptually, it was the same as the study done by Humphreys. Some key differences. Bottom line is their conclusion, and that is they were looking at Cretaceous age samples, which means 80 million years old, and that's what the radiometric dating showed. So they did conceptually the same thing as the rate study. They had a well, they sampled it, they measured the helium, they went to their lab, they did a couple of diffusion studies, they created a model, and then they asked, can we explain what we observed in the field based upon the model we created in the laboratory? And their bottom line conclusion is, yes, we have excellent agreement that this all worked. There was no problem at all with explaining how these zircons could retain helium for 80 million years. It's just straightforward application of scientific principles. They got this answer, and they said they used this word in their conclusion: excellent agreement between their model and what they observed in the field. So when anybody says, how can, or when you hear the claim, rocks cannot hold helium for millions of years, I would just ask a simple question: says who?
Mm-hmm. Yeah, why?
Right?
Yeah,
Humphrey,
why?
Yeah, okay. Humphrey says that. Wolf and Stockley say something different. Now, something interesting. I've never seen any critical analysis of the Wolf and Stockley paper by any younger creationists.
Mm-hmm.
In other words, no one has ever shown me why their data is wrong or why we shouldn't believe their study. Now, if I compare the two experiments, one of the things just to note right here is the sheer amount of data. In the rate study, they had 6 samples. In the Wolf and Stockley study, they had 110 samples.
That's a huge amount of samples that they
okay.
had.
In the rate study, they did not measure the uranium or the lead content. They just kind of assumed the value based upon the sample literally a mile away, down the well. They didn't really size them correctly. They just said the size is roughly in this range, and they had a whole pile of crystals that they measured and not one. In the Wolf and Stockley paper, they did single grain experiments where each single zircon was measured, length, width, all of that. The uranium content was measured, the thorium content was measured for each crystal.
Yeah, and that's a huge note, though.
On a crystal by crystal basis for 110.
That they have not refuted in the academic literature, Wolf and Stockley. As a matter of fact, it should be noted that I've never seen, at least as far as Humphrey, publish anything on this in academic, in any kind of scholarly journal. And to note, you did. Matter of fact, I'm going to promote you a little bit here. You went out of your way to even go to the Creationist Journal and say, hey, look, I have this paper. I would invite you to read it and publish it. And they refused to, only because it contradicted their findings. Not that they found anything wrong with it, but you did have it published in a scholarly journal.
But
you actually had yours published in a scholarly journal. There's not. Nothing they have is ever published in any kind of scholarly way. And I think that's something that's very telling.
Well, and even look at the last time we met. I mean, you invited Humphreys to join this so we could have a head-to-head debate. I mean, that's kind of your gig, right?
Yeah, and we get. And by the way, Humphreys is not an easy person to get along with. He is. It took me a long time to get into his good gracious because I hate to use the word paranoid, but he really thinks that everybody is just evil and have to get ring with creationists and things of that nature. So it took a long time to ingratiate myself with him. I have another friend, Dr. Jonathan Sarfati. who is really big on creation.com. I think he actually owns the domain, I think, but we get along exceptionally well. And matter of fact, just so Taylor knows, I'll do a little self-promoting here. In creation.com, there's an article called Atheism is More Rational. On creation.com, Taylor, by Jonathan Sarfati, he cites me at the very bottom. He cites my paper on the presumption of atheism by way of semantic square opposition. So he liked that argument. Sarfati liked that argument. He's a young earth creationist. We do not agree on young earth creationism. He knows very well we do not agree on young earth creationism. But the logic that I use in my paper is logic, and logic is subjective. And so as a creationist, I respect when they do that, say, oh yeah, this is correct. I reviewed it. Other people reviewed my paper. And, you know, so people can't just say that I'm bashing on young creationists. I happen to get along with many of them because, as you said, I want to talk about the science. I just don't want to sit there and attack young creationists. I want to say, okay, what is it that you believe here? What's the data for it? What's your evidence? And let's talk about it. And that's exactly what we're doing, because they're putting this forth as evidence when we're finding out, though, in reality, they made far too many mistakes to even remotely make their findings credible. But I just wanted to let Taylor know and other people know that watching. Creation.com, they're like I said, they promoted me. They literally, and I'm also on Reasons to Believe. I did a show with them for a year. So I don't want them to come back and say, oh, look, it's just some kind of evil evolutionist dumping on young creationism. It's not. We're talking about the science here. So
yeah, and see, the unfortunate thing is Humphreys didn't join the debate.
Yeah, he won't go live.
He didn't. But then he did review things and posted a rebuttal, and then you put that on your website. Mm-hmm. He took that rebuttal and then went to the Journal of Creation, and they published it. Yeah. I mean, it was
errors and all.
Past review. I mean, from the time from the publication date to the time we had the show was the time it took for him to compose the manuscript, get it through review, and get it published.
Yeah. But see, here's the thing, though. They're when they mean peer review, they mean some of the creationists read it. That's it. Yeah. That's the process. As a matter of fact, because they should have caught the math error that Humphreys had, that you caught and that you put in your appendix in your paper. By the way, thank you so much. I was really honored to even see that you put my in the acknowledgement. I was humbled beyond belief. That was very, very kind of you, to say the least.
Well, I'm very appreciative because, as you realize, I put in a lot of time and effort, but I've realized there's not been very many outlets. There's not been a forum for me to even share what I know, and that's kind of unfortunate.
Yes.
And then it's for a lot of reasons. Number one, the Young Earth Creation forum, they will not allow me to tell my side of the story. To finish the story of Humphreys, he got his rebuttal to the last time I was on your show. He got that published in the Journal of Creation. I tried to publish a follow-up article, and they rejected it. And then I did a major rewrite to make it, let's say, more palatable for them, and they rejected that as well.
That's very telling. That really is.
The point is, you will allow Humphreys into your forum. You will put his material on your website without question, but I'm not allowed the same opportunity to speak in their forum.
Well, because the statement of faith by creationists, and they all have it. Institute of Creation Research, creation.com, all have, and they have to abide by this. If there is any scientific evidence against the young earth, which is all of it, they have to ignore it. They have to say it's wrong. They cannot accept anything that refutes a young earth creationist position, which again has recused them from being in the scientific domain, in my opinion. It has taken them out of being called scientists. I will never call any of them scientists. They're educated. I know, like, for example, Dr. Sarfati is genius level. That dude is smart as can be. But he, in my opinion, has taken himself out of the academic arena for science because he has willingly said, well, anything that goes against the younger creationism has to be wrong. And obviously Humphreys and Baumgartner and Snellings have all taken that same approach.
But it goes further, Steve, because my manuscript, I carefully wrote it in a way where I would not question the young earth. Formulated more in fact, the final version was a lot like my Perspective on Science and Christian Faith paper. Basically to say, here, I was talking primarily about the Wolf and Sockman paper, that here's a piece of evidence that contradicts your accelerated nuclear decay helium diffusion study.
And they don't want to address that. But
and we need to look at this data.
That data they
and
never
I'm not
addressed.
Questioning, and in fact, I didn't question the age of the Earth. I did put a question mark behind accelerated nuclear decay, and I said you need to look at this data. I tried to make the conclusion as non.
I love the way you did that too. And you, I think you were published in the philosophy was it
Perspectives of Science and Christian Faith.
Yeah. Perspectives of Science Christian Faith, which is, it was just a scholarly journal, but it's very telling that they were willing to publish your paper because it was correct, vice the Journal of Creation, which again doesn't really care whether it's correct or not. It doesn't lend evidence to that for their position. That's it. And it could be completely wrong, because I've seen many things in the Journal of Creation which are just mind-blowingly wrong. Matter of fact, I think Dr. Henke, you have it pulled up right now, which I think is a big, to me, this is a big issue, that Humphreys made a major math blunder. He did admit that he interpreted it wrong. I have that email from him where he did acknowledge it. But my position is, if you've acknowledged that it's wrong, shouldn't you go back to the original work and correct it and edit it and let people know? Because they have never gone back and revised anything on this. This has been no movement on this since what, 2002 probably, 2010 at the latest. Matter of fact, the only reason I had a resurgence is because I had, brought you gentlemen on to talk about this, and that got a resurgence with Humphreys and creationist movement. But other than that, there has been no movement on the rate study whatsoever.
Yeah, the rate study ended in 2005, but that's when the fireworks started. And again, not only have old Earth creationists and secularists criticized Dr. Humphreys' work, but a lot of young Earth creationists. There were a series of papers by Freud, I can't pronounce his name, and Ackridge in 2012 and 2013, criticizing Humphreys and the accelerated radioactive decay claims. So,
but they haven't given up on accelerated decay yet. They still think that it's plausible. I mean, the problem with accelerated decay is we've known by physics that nothing under temperature or pressure is going to change the rate things decay. We don't know. I don't know any process that's going to change how things decay, the rate of it. They're constant. Matter of fact, if they weren't, again, a lot of stuff wouldn't work properly. And so they're positing something that is so outside the realm of actual science for this accelerated decay. But again, if they have evidence for it, that's how science works. And I love that approach. Is okay, if you claim this exists, what is your evidence? This is by any strict measure of evidence, the helium diffusion rate is probably the best they got as far as demonstrating accelerated decay, even though we know it's completely wrong. I don't think they have anything else. They literally have nothing else to latch onto other than, it must be accelerated decay because God made it that way. That's it.
And with Snelling, he definitely recognizes it's not going on in meteorites. So, why? Why are meteorites 4.5 billion years old? And Snelling concluded, well, God just made it that way.
Right. It's so funny that they have gotten to the point where they have to acknowledge the science is correct. There is an appearance of age. Matter of fact, many creationist scientists have told me this. Yes, there is an appearance of billions of years. However, they're like, but we can explain it why it looks old by this ad hoc mechanism that they've never had actual real evidence for. But that's the big thing. They admit, Rates even admitted there is an appearance of age. And of course, they don't subscribe to what's called the Omphalos hypothesis, that, God created the earth last Tuesday with the appearance of age, because that would make God dishonest. And even creationists don't want to go down that route. They don't want to make it say, God created the earth 7,000 years ago and the universe 7,000 years ago, but he created it to deceive people with the appearance of age. That's not something that they really want to argue. So they have to admit that, yes, there's an appearance of age, but how do they explain that? Well, one of the things that they use to explain it is the very topic that we're talking about right now. But unfortunately, it doesn't get them to where they want to go because, again, there was at least almost a dozen things they got wrong, major errors. It wasn't just one or two. There was 12 major errors, or 10 major errors at least, that I can think of. But I think this was a big one that Humphreys made that you have on the screen right now, if Gary can talk about real quick. Because this was in your paper.
Do you want to talk to it?
This has to do with the Arrhenius formula and the derivation that he had for his model, right?
Yeah, with logs and I can scroll it up here. Because
he, like I said, he admitted to me that he interpreted it wrong. And I have that email, so it's not like, you know. And he said, yeah, go ahead. He told me before I can show all his emails, but he didn't correct it. He didn't go back, and this is what I find to be just a bad taste in my mouth about creationism is that, okay, they admitted that they made mistakes. When you do that, go back and fix the original stuff, because then you have these creationists now that go back and look at their, like on creation.com and other things, and they go, oh, look, this is how it is, not realizing it's already been addressed and they've already acknowledged it's wrong. You know? All right, so what do we got here? This is the domain modeling that he used, correct?
Correct.
For diffusion rates, which, again, it's been long standing that you don't add diffusion rates, right? It's something you can just add together. They're not additive like that.
No.
Okay.
Yeah. So Kevin, you can go through the math. I'll just say, when I saw this equation, it's unlike anything I'd ever seen. I mean, it looks innocent enough, but you're just adding these two rates, and you're not. And you
had asked Dr. Humphreys last time you were here for his derivation of this. This is how it came about. You were streaming, and you had asked Dr. Humphreys, how did you derive this equation? I've never seen this equation before. And he showed you how you derived it, and unfortunately his derivation was wrong.
Yeah, there's just to simplify things, we got some substitutions here. We'll let A equal the first part of this equation, and B equals this. And so he's saying that the diffusion is equal to A plus B. And okay, I'm having trouble with my pointer.
So
here.
he's just basically saying the diffusivity rate is just the addition of one domain plus the addition of the other domain.
Right. And this is where he made the error. He was adding here where he should have multiplied. And you can do this. Let's just take a simple example of using 100 and 1,000. Okay. If we multiply them, we'll get these lateral log numbers, and we add them together and they work out. But if we use Humphrey's original approach and add them together, they don't work. So he needed to multiply here instead of add.
I even put it in Wolfram Alfram so she can see. I'm sure she's had some math before. Is that if you have the natural logarithm, the rule for that is that you can take the natural logarithm by the product, and then you can get, so you have ln A and product B, you can get ln B plus ln A, and that's true, but you cannot have ln A plus B and do it that way. And that's a huge mistake of applying the rules of logarithms, natural logarithms, because it has to be multiplied. If you guys can't see it, but the outside I'm showing, it says true here. Natural logarithm A times B equals natural log A plus natural log B. So if you have an addition there where you just take natural log of A plus B, you're not going to get the right answer. And that's what he did. He made a math error by he misapplied the rule of logarithms.
Hey, can you hold it there? Can you actually scroll up to your reference? Just a rather amusing, right there, an amusing side comment, because in my perspective on science and Christian faith paper, I presented a similar argument with less detail. And then when Kevin asked if he could use it in his webpage, I said, sure, go ahead and use this argument. But he wanted to make it, add more steps to make it more rigorous. And then he approached me if I knew of a reference for this kind of work, because I provided no reference in my paper. And the reason is, how do you provide a reference for something that considers to be high school math? I mean, I don't consult the journals to do basic algebra.
It's so wrong. It's not even wrong, right?
To Kevin, I can't even think of a reference.
Yeah.
High school math.
I found a high school,
and that's exactly what you did, right?
What's that?
I used a middle school algebra book.
Yeah, his math was so wrong, it wasn't even wrong. In matter of fact, I like the way you did it in your paper, because you could visually see, and this is a big takeaway, the multi-slope curve, when you have the high domain, the intermediate region on the knee, and then you have the low domain. If you use Humphrey's math and that he responded to you, his paper that he put in the journal Creation, it ends up as a linear equation, not two slope. And I'm sure Taylor could understand the difference between a line and a curve. And so when you have these two lines that have this curve on this knee, the model for a line's not going to be anywhere near that. Now, he said he did it to approximate, but that doesn't even work out right. But you can definitely see using his math, it produces a linear equation, mx plus b. It literally produces a line. So it cannot be. It cannot physically be a mathematical derivation from what he started with, because the math's wrong. The way he applied the logarithm rule is wrong. So this is a very visual way to see. You don't have to know math. You just have to know, does a line represent these these lines together? No, it clearly doesn't. It doesn't represent the actual image that we have of the high domain line, the curve, and then the low domain line. So he should have recognized it immediately that his equation derivation did not even come close or approximate what the findings of the data was. But it took a long time for him to recognize he made some errors. Again, a year of corresponding with Dr. Humphreys, he finally again admitted that he made mistakes, but he never went back and corrected them. So.
Yeah, and Humphrey's attitude is rather nonchalant. It's like, yeah, I made a mistake, but it's not that important.
But it is important. It is a major mistake. One is math, and two, he had argued. He even told me initially he didn't make a math mistake, and it's like, well, yeah, you did. I mean, I'm not trying to argue with a PhD in astrophysics, but this is logarithm stuff. This is high school level stuff,
yeah.
And you can see visually that, as you pointed out, it's a straight line on the Arrhenius plot.
Now, his argument is that he didn't use that equation directly in his model, which is true. But here's my point. It goes back to what I said, to go from the laboratory data to the field, to extrapolate over that much time, because you only have about 2 days to observe this material in the lab, and you're going to try and project over thousands or millions of years, requires a thorough theoretical understanding of the material science. Now, if somebody can't even get a simple math equation like this right, how well do they understand at a conceptual level? You see, you can say, yeah, it was a math blooper, it was a math error and everything. But to me, the more serious issue is that means his fundamental conceptual understanding of what's happening there is wrong. Mm-hmm. And that's what concerns me more. It's not just, yeah, he made an algebra mistake, but his way of thinking about the problem is fundamentally wrong. He doesn't understand material science.
He doesn't have the technical expertise you have.
Mechanics. He does not understand these things, because anyone who did would not even have made that mistake, or they would have caught it right away.
Would somebody, okay, so as his background's in astrophysics, would he ever have to take something like collision theory? Would that be a subject that he would ever...
Presumably, even at an undergraduate level in physics, he had a class in statistical mechanics. Mm-hmm. I would imagine. That's in most courses of study.
The Arrhenius formula should be second nature to him in any way, because you find that in chemistry. You find that in any physics.
Yeah. I mean this Arrhenius thing, which for those who are not familiar, it basically says that when you have a thermally activated process, the rate of dependence on temperature has a very specific mathematical form. Yeah, anything like that. You can go, that equation 3 will do it. It has a very specific, a lot of processes in chemistry, in physics, reactions, and things like that are thermally activated, and diffusion is one of those. You have a very predictable theoretical basis for its temperature dependence. And it's basically whatever that parameter is, in this case, the diffusivity, it's equal to a constant, in this case, the d infinity, times an exponential of a quantity called an activation energy, in this case, the Q, divided by a constant, R, times the temperature in Kelvin. And this is the fundamental, this is how a physical process behaves fundamentally, a thermally activated process. Now, in the rate data, you didn't have a straight line, you had 2 lines, which says you have 2 separate processes happening independently, and you have to treat them independently. You can't just lump them together. Mm-hmm.
And that's exactly what he did. He just added them together.
Is fundamentally wrong, because that's not the thermal activation. The thermal activation follows this form. Mm-hmm. And if you see more than one slope, then you have more than one processes, which in a crystal, that's not a surprise. You can easily account for, there's going to be some states that are going to be able to hold the helium more tightly and other states less. And I can see different activations, but you have to treat them separate. You can't lump them together. And this thought that I can lump them all together and it applies to all the helium is so fundamentally wrong. And the fact that he couldn't even provide a simple proof and made fundamental high school algebra errors, to me shows not just the math error, but what is more disturbing is the lack of fundamental conceptual understanding of what thermal activation really means. You don't understand statistical mechanics if you make these kind of errors. You just don't understand how materials behave.
And that's something that, like I said, a Taylor, I don't know what grade she's in, but it probably junior high or something. Obviously she's not going to know probabilities. She's not going to know steric number, what a steric number and frequency factors and these coefficients and real gas law and Boltzmann constant. All these things you learn in physics in college level. So I don't think she's ever been exposed to any of those things. So she has to go rely on the fact that, Humphreys has a PhD. He is a legit PhD. And so it is basically an argument to authority, if anything else. It's sad because it's not an expert in this particular field. You are. You are an actual expert in this particular topic. It doesn't mean you're right. That would be a fallacy as well. But it means that you have a level of understanding. There's no possible way that, well, one, a 12-year-old is going to have or something like that, or a layperson is going to have, but probably something that's going to be outside the domain of even an astrophysicist. It's because it's a very niche type of subject. And this is why PhDs do specialize, because that's their area of expertise.
Well, and let's take it a step further. You say PhDs. Some of this diffusion stuff, I did not know even through my PhD. It was working in the semiconductor industry.
Semiconductor stuff that which actually utilized, right? I mean, that's probably why you had to learn it, because it applies in the science, in the social, in the solid state.
That's one of the things. Humphrey is relying upon his general physics background, where you have these simple models of diffusion, and you move on, because that was not an area of focus. So he has really that general physics background. Mm-hmm. A lot of these advanced modeling things I didn't learn during my PhD study. I learned during my summer internship at Motorola.
I just had to learn basic chemistry stuff and reactivity, rates of stuff.
In classes, you can have these nice little assignments, and you solve this problem, and you learn this. In industry, you got to make it work. Mm-hmm. You got to find a way to make it work, and if it's not working, you need to understand why.
In other words, they wouldn't hire Humphreys for what you do.
Models, I mean, some of them have like 30 different parameters. It's mind blowing how complex solid state diffusion can be, and this is for silicon, a simple monoatomic crystal that's well understood. And it took the semiconductor industry decades of research with hundreds of experiments to have the ability to model diffusion accurately.
It's complicated. Yeah, and that's the kind of the takeaway. I mean, I know we're running kind of long here, so we'll start to wrap it up. But the takeaway, it's very complicated. Matter of fact, there's other questions he had asked, and we'll get to those in time. I was going to do one show on the whole video, but it's just obviously this one particular topic requires so much, and we didn't even scratch the surface. The other two videos we have, they were 4 hours each, really dived into the complexities of this topic a lot more, and some of the errors that they made in the rape program. I mean, the takeaway is that you have people that are not experts in this field trying to tell people about a topic in order, in my opinion, to mislead them from actual science, only because they start with the premise that the Earth is young. They start with the conclusion. They don't get to the conclusion. They start there. And that is the antithesis of how you do science. So what? Any other errors they want to talk about real quick before we wrap it up? Some of the like bullet points. Because I think the main ones, I do think, obviously, misidentifying the rocks and getting the domain modeling wrong is just massive. But what? Any other thing else that they did? They bungled.
Pressure is another issue. There was a study by Dunai and Rosely where they looked at the diffusion of helium in garnets, and garnets are other silicate minerals that are similar to zircons in that they're very hard minerals. And they actually did their lab studies at high pressure, up to 250 bars. and high temperatures. And what they found was that if these minerals are under 250 bars at temperatures of 700 degrees Celsius, which is about twice as much as the zircons at Fenton Hill, the helium would take tens to hundreds of millions of years to diffuse out of those little garnets. And so it would be interesting to do these zircon diffusion studies or studies under high pressure lab conditions. Now they were limited to 250 bars, but unfortunately, at Fenton Hill, the pressures, the rocks where these zircons were at pressures of 200 bars, a little bit lower, and then higher up around 1,000 bars.
All right. So what would you like to, if you guys got in a nutshell how to answer this question to Taylor where she can get a takeaway? I know Standing for Truth probably watched this and some of the other people. In a nutshell, how would you just answer this question without any of the technical stuff about why we find helium still in rocks that, according to the young creationists, shouldn't be in the concentrations that they have? In like a simple 1 or 2 long sentence.
The zircons are impermeable.
Yeah, okay.
And they're under high pressure.
Yeah.
And moderate temperatures.
So you say that zircons are probably not the best, thing to have a measurement of the age of the Earth. I think you had pointed out, Gary, that all it just tells you is how much helium's in there. It doesn't tell you the age of the Earth.
Yeah, and I think the message is to do good science, you really need to pay attention to the details, because the conceptual argument is, well, helium diffuses fast and therefore rocks can't retain it for any long period of time. That's a qualitative statement. Qualitative statements really aren't much value in science. What's important is quantifying things. And when you quantify things, it requires doing all these things correctly, the math right, the experiment right, and everything. And the takeaway is you can demonstrate in this particular case that when you do science right, you get an answer that supports an old Earth. Mm-hmm. And we walk through a lot of that. And then so going from this conceptual statement that, helium diffuses fast and rocks can't retain it for a long period of time, that's purely qualitative. Yep. Science is really about quantitative things. That's why the math is important. That's why the modeling is important. That's why doing the experiment carefully is important, because the numbers are important. Because you can talk about concepts, but until you put numbers to it, you really don't have an idea of where you stand. And I would hope that people today would realize, number one, people have put thought into it. They have done the math, and it comes up with an answer that shows, yes, these zircons can retain helium for quite a long period of time at normal geological conditions.
So it's just not the evidence that they're looking for age of the Earth nor for accelerated decay. I'm going to leave you guys with this. This is what Humphrey, like I said, Humphrey has sent correspondence with me for a while. He gave me full permission to show his stuff. He actually advocated for it, but he said, because I may have misunderstood something, but he said he misunderstood me. I said Dr. Loechelt did not correctly report my derivation, not that not that his math was incorrect. So he even recognized your math was correct. He recognizes that in your paper you got it right. Okay, he did not report that I intended my equation A or his equation A1 as approximation, nor did he report that I'm proposing that taking the natural logarithm of A1 should yield A2, which again he did get that wrong. He says, nor was my math incorrect. He knows now his math is incorrect. But this is the takeaway. He says, however, thanks to him, I now see that my interpretation of the equation A2 is incorrect. It does not give the two-slope diffusion curve that I wanted. So he did recognize this, but my argument is go back and fix this. Dr. Humphrey should go back and fix this, because we have people out there that are just now learning about these topics, like Taylor, who's probably never heard of helium diffusion rates, growing up or anything like that. This is probably something relatively new to her. She probably read it off some kind of creationist page. She's unaware that even Humphreys is aware that he made some massive mistakes. She's unaware that the rate study made some massive mistakes. She couldn't get the type of rock right. So this is why when you have experts like you two that come in and say, hey, look, let me explain this, that they got stuff wrong. It's not a matter of belief. It's not a matter of faith. It's not a matter of theology. This is the science. this is what they got objectively wrong. And it corresponds to all the other experts that have done independent analysis on these things. And that, I think, is the biggest takeaway. And I really do hope that Taylor gets into science and learns it properly. Wayne Philmore, who left Young Earth Creationism, eventually went on for a while to become a science teacher. And that was amazing. And he did a story about his conversion on BioLogos, about how to debate changed his life. His debate with me changed his life because he recognized that Young Earth Creationism was wrong. But he didn't leave religion. He's still a Christian. So you don't have to give up everything about science in order to maintain your religious beliefs. They're independent of each other, in my opinion. So with that, if you guys have any questions, we'll get to them on my channel later on. I'll probably do a follow up on my main channel. I do have, like I said, Dr. Ross joining us on the 27th for the Starlight Problem to talk about Jason Lyle's asynchronous, light transmission kind of convention that he's proposed. And we will be talking about biology with some biologists on evolution, which, before we leave, one thing, this was actually a video on asking about evolution, right? This is not evolution. Matter of fact, this has no relationship to evolution. You could deny evolution and still accept physics like this. They're independently things. And I don't know why they ask people that understand biology physics questions like this,
Yeah.
It should be noted on that because this has nothing to do with biological evolution whatsoever.
Yeah,
absolutely.
Yeah. All right, guys. Anything you want to promote? I guess I have all your links at the bottom in the video description. I hope everybody goes reads them. But is there anything you want to leave us with?
Well, I want to thank you, Steve, for having us. I should just point out that my essay, you first of all go to Talk Origin, and Talk Origin has been very dormant lately. So I moved this essay and updated it.
It's so good.
Over to my website, and you can click on that here.
It's so good. There. Yeah, it's in the video description. Your essay and Dr. Loechelt's paper are just, I think, definitive works on this particular subject. And I don't think any Young Earth Creationist is going to be able to ever refute what you put in this paper here and what he put in his. It's just not possible. I think they're going to just kind of let it go. I think they're going to probably not really address anything and just let it fall by the wayside like they have let other things when they been pointed out that they're wrong about it. So, but thank you too.
We'll see what they do with their Hour project.
Yeah, I heard they got something else they're trying to get funding for, the Hour project, but I don't know. Have they got funding for it yet?
They're trying to raise funds for it. I don't know. We won't hear any results for probably 2 to 3 years.
Yeah.
But yeah, the Creation Research Society is raising money for Hour, which is helium outgassing of uranium radioactivity. And it's because people like Freud and Ackridge were criticizing, and others, Hartnett, Williams, other creationists, Young Earth creationists, were criticizing Humphreys for not having more zircons at other locations to verify his accelerated radioactive decay claims. And so the Creation Research Society is going to try a study with more zircons at other locations.
All right, we'll see what they got. But like you said, it will be a few years down the line. So
yeah, it will be.
All right. Thank you all for watching this. You guys got comments, leave them in the video comment section, and I will try to address them. Like I said, hopefully Taylor will be able to watch this and address it. I know it's quite long. I know it's a lot of technical stuff, but I think you have to recognize that it is technical and not some 1 minute answer that you're going to get by calling up, a YouTube channel like Standing for Truth and say, okay, well, here's my question, and expect a really concise answer in a matter of a minute. It's just not going to happen. It's way too complicated for that. So I want to thank both of you gentlemen once again for joining us on the NonSequitur Show. Great debate community. And we'll see you guys another time. Good night.
Yep. Thank you, Steve. You have a good day.